Welcome everyone, good time of the day, and I welcome you to the series of online technology meetings provided to you by EPIC. And today the topic of our meeting is photonics and quantum sensors. Let me first remind you that EPIC is the largest photonics industry consortium in the world, comprising over 800 corporate members inside Europe and also outside, and spanning over the whole range of value chain of industry of photonics. Today we have an exciting agenda. We'll hear from 6 speakers representing different companies and the research entities. We'll start with a keynote talk by Christopher from UK National Quantum Technology Program, followed up by Globe Photonics, Qnami, Ixale, Novovis, and FineTech contributions. We'll have a very interactive discussion, so I welcome the audience today, and I welcome you to ask questions. You're also welcome to turn on your cameras to make it a more interactive and friendly environment. And I'm glad to have all of you here with us today. So, in fact, with no further delay, I'd like to invite our first speaker, Christopher, here. And Christopher, please introduce yourself and get ready with the presentation.
Afternoon. Thank you very much, Ivan, and thank you for having me here. EPIC, it's a great consortium. Been members for a long time and gone to plenty of events, so it's lovely to speak. I think this is the second or third event I've spoken at over the many years, so it's good to be back and be keynoting this time. I'll share my presentation, which is going to be on basically the trends that we're seeing at the moment in quantum, in sensing, imaging, and timing. So as Ivan's already mentioned, so my role is that I'm head of business and technology within the UK National Quantum Technology Program. I specifically specialize in imaging and sensing and now timing as of last Christmas. And really my role comprises of bringing together business and people and finances to develop the UK landscape in quantum. I also do a fair number of delegations on kind of a global level. So I've recently just come back from Japan, going back out actually again in a few weeks' time. So that's been exciting. I know a number of you from Japanese-based companies online today. So I look forward to speaking to your colleagues there. And if there's anyone that you would like me to meet out there, then please do say so after the call. But broadly speaking, I think it would be great to talk about where this area is going at the moment. And I suppose just to start off from the UK's perspective, quantum is still a small sector in the grand scheme of things, but it only started really in 2014. And it's amazing what we've been able to sort of progress forward in terms of how much we can market and the areas that we can assess here. I always made the joke of everything can be commercialized nowadays. We even have a space sector, so we can commercialize space itself. But nonetheless, let's sort of dive into some contextual numbers. At the moment, broadly speaking, there's clearly an error bar, quite a significant error bar in this. The UK photonic landscape is valued at about 20 billion per annum in terms of its impact to the UK economy. And we see around about a 2 billion valuation in quantum on that. So the main sort of takeaway from this is that the UK, that ratio is very, very high, that sort of 10-to-1 ratio. And I mean that high in a context of the global ratio. So we see other economies, the main one to sort of point out is the US. It's far closer to that sort of 100-to-1 basis. It's important also to recognize that different countries have strengths and weaknesses in certain areas. The US is far more involved from a semiconductor basis than the UK is, for example, and there are different areas in quantum that the US focuses on. So timing, for example, And the UK is pretty strong when it comes to sensing and imaging, particularly imaging has a historic context within the UK. In fact, the last data that I had
Eu estou a tentar
hands-on
desligar isto, não consigo.
was back in 2023. And Europe actually had the biggest investment in the quantum market in sensing and imaging. So pretty darn strong there. The other thing, just to give sort of some context for this talk, is where the industry is going at the moment, again, relative to photonics. So in photonics, we largely see a pretty strong revenue stream at the moment. The unusual factor is a bit of a stagnation in terms of jobs. So not that many new jobs coming in, but per job, they're making more money. We see a lot of M&A, so mergers and acquisitions happening at the moment as well. And that is particularly dominant in the quantum market. That's not massively surprising, quantum being a sort of a new area, but we see somewhat the same. The job growth is slightly more in quantum, but only slightly. So again, we're seeing more of the few people who are involved are generating more income. So most businesses are focusing on their sort of value add per product is generally the trend that we're seeing. And then one of the biggest factors at the moment in the world is the back and forth with AI. So in terms of startups for 2025, by far and away, the most was in AI. In the UK alone, I believe there was about 250 AI startups officially registered in the UK, compared to about 25 in quantum. So effectively a tenfold increase, relatively speaking. And then a lot of the other sectors are somewhere in between there. But again, AI to outcompete even areas like life sciences, where startups are historically very strong, is pretty impressive. So no doubt a lot of the trends that we're going to see in quantum will be influenced by AI. And that might be in terms of power management, data management, giving additional axes for those matrices to look under. It's all going to be very, very important. To give a more concrete example, in imaging, for example, the use of LiDAR with quantum sensors is seen as a key thing for AI. It gives another dimension effectively to do their algorithmic approaches on. And then in the sort of the longer term, we're expecting there to be, well, relative stability in the immediate future, but a bit more volatility in the market. And this is mostly going to come about that a lot of quantum initiatives are government funded at the moment. And that's not going to disappear tomorrow. But sooner or later, governments are going to want their return on investment, certainly from the UK's perspective. We've been running our national programme for 11 years now. So we've been in this job for a little while. And you can understand why taxpayers want to see what they're going to get for their money. Not to say that they haven't been getting their return on investment in the meantime, but people are going to be looking for some more concrete examples. Now, this won't solely rely on imaging and sensing. Quantum computers clearly the headline on a global level, but certainly there'll be some expectations to have more and more products in this area. And you'll see some of that influence in some of the points that I talk about later on. So that's kind of where we are from an economic standpoint. From a product standpoint, in the quantum domain, I'm going to pick three sort of examples. So on the top, just talking about from a sort of detector standpoint, specifically, I'll talk about SPAD detectors. The image, by the way, is from the James Watt telescope, if anyone's particularly interested in that. But in SPADs in general, we're mostly seeing a pretty fierce competition on the patenting landscape. So a lot of people are building up their patent portfolio in SPADs. We know that Canon, for example, has been pretty progressive with this. Sony is sort of working their way through a lot of applications that they can patent through. And the interaction between industry and academia is heavily on the what do you have in terms of your IP, in terms of your patent portfolio at the moment. In particular, there's certainly a hunt for time-correlated single photon counting. This is mostly because a lot of the products on the market at the moment are time-gated. And largely, customers are looking for this because they want that performance metric, mostly in the time domain when they're doing LiDAR. They want to do high-resolution LiDAR. So that's really a push at the moment. There is a bit of an interplay there because some people are coming up with approaches where they say, actually, time-gated is okay for the majority of the mainstream markets, such as automotive. But we've seen a bit of back and forth on that sort of front. So I'm expecting that there's going to be a few time-correlated single photon counting detectors coming out in the next couple of months and years. And that kind of patent landscape will continue to be pretty fierce. The other thing to mention, just like in quantum compute, the conventional technology holds on strong, and your good old-fashioned CMOS detectors are still very, very good and continue to be developed. So one thought may be that conventional CMOS will actually hold out for a lot longer than expected. But sooner or later, these large semiconductor firms are going to have to pivot or understand the architecture that they're working on in the future. So that's an interesting space at the moment in terms of imaging. A little bit more on the sensing side, so our sort of step below are nonlinear optics, in this case, PICLIN. We're largely seeing a progression in terms of efficiency. Those efficiencies are a little bit slow moving forward, but they're still moving forward, and that's absolutely fine. And the supply chain is extremely strong. I should point out that Cohesion recently merged, and they're doing very, very well. So congratulations to them from a UK perspective. I know some of the colleagues might be on the call today. And more generally, and maybe they're the better people to speak to on this one, the roadmap is quite difficult to predict from a macroscopic sort of view with nonlinear optics. And this is largely because the applications keep sort of coming up from left field. Originally, you could use this in terms of an improvement from telecoms. A lot of people, in terms of sensing, use PICLIN to convert telecoms lasers to interesting wavelengths of choice. You have OPMs that are used. But we're seeing more and more, there's an interest from quantum comms, from compute in this area, and even as an alternative for more conventional technologies. So nonlinear optics is quite difficult to play out, but broadly speaking, it's doing very healthy. And I'm particularly interested in that area to see what comes forward there. And then finally, in terms of as a technology platform, you have Rydberg sensing. So the image here is of your vapor cells. And this is increasingly of interest, particularly to government procurement suppliers that we've been talking to at the moment. There's a lot of national security applications here, border control, etc., but also medical. And both of those areas are very much your public domain providers. And in a lot of nuance technologies, you see that government first as a customer is a really strong way forward. So we're seeing more and more of a growth in this area. Vapor cells are still quite hard to come by. There are a couple of companies that remain quite dominant here, particularly over on the American side. So there's more of an interest for Europe to be involved there. So if anyone knows of any good vapor cell suppliers, then let me know. I'm sure we'd be certainly interested as a UK market, but broadly speaking, I think a lot of people in Europe would be interested in making more of those on this side of the pond. But also we've seen a lot of the laser companies be quite interested in this space. Anyone who works on the atomic side on sensing will know that lasers are key. Often people have a hell of a lot of lasers when they're working with these. And it's actually the optical side that does a lot in terms of your size, weight, power, and cost requirements. So the influence of NKT, Toptica, so on and so forth is actually quite strong in this market. So It's interesting from a geopolitical kind of standpoint because at the moment you've got the Americas that make the cells predominantly, but Europe is actually very, very strong in terms of its optical input. So you actually have quite a control over this market. And we're seeing more and more of these come to a sort of commercial head, particularly in the healthcare domain. Some good example of those within the UK. So those are some of the interesting developments from a technological standpoint and where they're kind of going at the moment. I'd be really interested if people have any other good examples with these technologies. I know that there's a hell of a lot more, and where your particular firms are going. I suppose as a sort of a plug-in from the UK, we're really interested in promoting these as well. So if anyone has an interest in broadening out in that space, then do let me know. I suppose one other thing that I would really like to talk about as a final sort of subject matter within my talk is where in this development does it mean from a product standpoint? And most people are familiar with sort of technology readiness levels. It's not quite the same, nor is it sort of a manufacturing readiness level. It's kind of where do you sit on your vertical, I suppose, in your market. But generally, we've seen a shift in quantum from these kind of element-based components through to general components, devices, systems, and then ultimately onto platforms. Platforms is not usually actually something that quantum and photonics touches. And by platform, I mean an entire system. And we hope to see a little bit more of that integration. There's a bit of a gap still. So what I mean by that is that, for example, if you are doing a LiDAR-based approach, how do you map onto things which already exist in that industrial environment? You know, are there any standards or any typically used software that you can interlink with very, very quickly? That interface is still a little murky from the general perspective of the market. But more and more, we're starting to see pretty concrete devices and over on to systems themselves. Now, one thing that we're expecting to see when the market matures a bit further is actually the technology to sort of flow back the other way. So this is usually when you have system integrators, which are pretty big markets in themselves, sort of tier one suppliers, become very, very comfortable with devices and components. And they can actually take on those as OEM parts and then build the systems and the platforms themselves. So we haven't quite seen a dramatic sort of shift in that yet. So there's still a bit of growth to expect in the quantum technology markets. But certainly we hope and expect to see that in the sort of horizon of about 5 to 10 years. Not to say that it's not happening at all, but more on a general scale. Most people are still pushing for more and more quantum-based systems. Now, I mentioned in terms of previously about the back and forth with AI and where countries sort of stand. I think one of the key things with this in mind is that I think if you are a firm that is able to produce concrete systems in the sort of the quantum domain, you're going to do really, really well. So I'm aware of a couple at the moment, but that skill set has not been particularly strongly advertised in the sort of the quantum space. So if you're thinking as an organization, hang on a minute, I can take a component to a device and a device and stick it in a system and meet an end user need, you're going to do really, really well over the next couple of years in the sort of the quantum and photonic space. Certainly, the UK government would be happy to fund you. And that's a lot of where our funding sort of direction is going. I would also say that if there's any sort of learnings or specifications that you think are unrealistic, it's worth sort of putting those into the standard committees at the moment. I know expectations are high at the moment in quantum, and there's a level of management there. But again, it's valuable to have this kind of feedback. And then finally, if there's anything in the sort of the long run, when we expect this kind of flow back to more element and component based, in terms of infrastructure, a lot of countries get quite worried about this because they realize it needs long-term planning. And without sort of devolving into a conversation about semiconductors, having input about what the infrastructure you need to build those elements and components is valuable as well. But at the moment, just to, I suppose, tie off, if you feel you're confident to build system base, you'll do particularly well. And I'd be really interested to hear more about people that can do that. So I suppose to do the epic question, to kind of tie off before I get inundated by questions and complaints about my talk. The thing that would be great for me would be if you have if you've heard anything that I've talked about and you go, actually, I know a fantastic supplier that can do that. Maybe they're based in Europe. Maybe they're not even based in Europe, but they have an interest in the UK. That would be brilliant. We are really in demand for that at the moment. And then in terms of what I can do for EPIC members, my role certainly sits at the interface between sort of academia, industry and government. And government is looking about where it's going to spend its pennies next. In particular, they want to have systems that give confidence to their arm's length bodies, that they can get them into BAU, business as usual, really quickly. We constantly get put forward technologies that say, okay, yes, if you've got a PhD in quantum mechanics, or you really know the ins and outs in photonics, you can work with us. But really, they want someone that, a builder, a plumber, a nurse, these types of individuals can interact with, that is a quantum device that gives them a quantum advantage. So if there are any systems like that you're aware of, that you think a government or a large public body would be interested in, then I'd be happy to hear about that. I think I could probably help you out there. So that's a very sort of whirlwind talk, trying to keep to time there. And hopefully you've got some questions for me. So thanks very much.
Thank you very much, Christopher. Great presentation. A very interesting perspective you take on the development of quantum technologies. So I'm sure many of our members and guests here didn't hear this perspective yet. So yeah, I'm sure there will be a lot of questions. Let me actually already pass the word to people in the audience. Maybe Bas Claver from DEMCON. You can start.
Yes, thank you very much. Thanks, Christopher, for a very interesting perspective. And I was triggered by your saying if you are a system integrator or a module developer, then you have a bright future ahead of you, because that's exactly what we do. So I'd like to somehow get in touch with you and follow up on this, see if we can explore if there are domains where we can cooperate. How do we do that?
Excellent.
I'll be happy to put you in touch.
Yeah, brilliant. Thank you.
Okay,
That's
thanks
fantastic.
a lot. Yeah, very good.
Thanks, Bas. And the next question from Nick from Quill, please.
Hey, Christopher, good to see you again. Quick question. Vapor cells. Can you kind of talk a little bit more about what areas of interest there are there, or what specifics? Lab experiments or stuff that goes into products, or both? Both are fine.
Ultimately, both. I think a lot of the lab experiments are going into products now. The biggest problem, so I suppose when I say vapor cells, all species are generally of interest. Yeah, rubidium is probably the most common, I would say, if I had to pick one, but broadly all species are pretty happy to deal with. Manufacturing is difficult. The sort of getter materials and things like that, we're not particularly good at here in the UK. I think I'm not going to offend anyone by saying that. And companies like QSpin, have long been the company of choice. And congratulations to those organizations. But there is a want to diversify the market, particularly on inside the UK, and that's both from the firms that are buying from them are still happy with their supply, but they just want to have resilience if that supply gets disturbed. And equally, there are a lot of organizations that want to sell into defense and security. And sometimes that becomes a real blocker for them. I'm sure we can all understand that the situation at the moment, you never really know what's going to be next on ITAR and so on and so forth. So that's the general outlook. It's that resilience of the supply chain, and the facilities and the expertise certainly seem to be a bit unknown on the European side. So if you know anyone that can make them on the European side, that would be great for us as well.
Does Canada qualify as Europe?
Probably at this point.
I'm kidding, but not really. But okay, that's great.
I think we would still be interested. I think that's a conversation that would still warrant merit.
For sure. Okay, that's great. Thanks.
Yeah.
Okay, great question. Christopher, I got another question in the chat from one of our members here. Maybe it could be good to bring everyone on the same page. Tell us what's the working definition of quantum in the scope of technologies? Maybe the one that also raises questions is quantum imaging. What is quantum imaging?
What is quantum imaging? Just as a broad definition.
Yeah. What is the working definition of quantum here? Where is the threshold between regular imaging and quantum imaging?
Yeah. Okay. This is an interesting topic, which I'm sure will offend someone on the call. But it's a valuable question. I think, largely speaking, people recognize that the controversial one is usually SPADs. So it's single photon. Is that quantum or not? It's generally been accepted within the quantum community, certainly within the UK side. I realize that across countries, that is not always the same. One good example, actually, having recently gone to Japan that I mentioned, despite they are sort of world leaders in camera technology, they don't largely see that as quantum. They focus a lot on things like NV diamonds, for example. I realize that's sensing. But I would certainly say anything single photon qualifies, broadly speaking, from a UK perspective. Another commonly used example in the UK from a quantum imaging perspective is anything that integrates your nonlinear optics in terms of entanglement or even correlation, dare I say, would probably count. There is not too much of an emphasis on the scope. I realize there has to be a boundary drawn at some point. You can't fund everything and be infinitely flexible. But the main point that I would always press upon is that if there is an advantage, and I don't even mean relative to conventional technologies in the classical sense, I mean relative to conventional technologies in the currently used sense. So if your technology, maybe it's quantum, maybe it's not, you could probably have a bit of an argument about that. But fundamentally, if it is better, we will have a look at it. We will take it very, very seriously as a national program, because the primary goals of the national program, as is true for most national programs, is making it economically beneficial and socially beneficial. There's no point being too particular about the definition of is a technology quantum or not if it's ultimately going to save lives or if it's going to make a financial sense. So that's maybe a little bit of a cop out on the question, but hopefully that sort of goes a bit of a way. Yeah.
All right. That's a fair answer. And then maybe I take the chance to ask the last question to you regarding, since you spend so much time discussing the market and the integration of quantum technologies, what's your take on the famous quantum winter? Will there be a winter for quantum technologies, and whom it will mostly hit, in your opinion?
Okay. So I think I can understand the worries about the quantum winter. I think that's very valid. I think most of the pressure lies on compute, given that most of the publicity has landed on compute. I think that there is certainly going to be a slowing down. That's just natural in terms of your hype curve. But I think the term quantum winter sounds a little bit more drastic than it need be. I think we will, like as I sort of, I suppose, touched on briefly, we'll see some volatility in the market, no doubt. But that's largely based on if these large funding bodies, government, see that transition to business as usual influences. I think imaging and sensing is actually pretty robust to that. Everyone recognizes that both those areas are going to be useful. They make clear commercial sense. Not even commercial sense, they almost make mechanical sense. If you want to build something, you typically need some sort of imaging and sensing attributed to that system. So I think we'll be fine. But certainly in the context of quantum, as it's known for computing, you'll see a bit of a cooling. But winter, no, I don't think so.
All right. Good to hear that. Okay, if there's no further questions for Christopher, I guess we thank you again for joining us today and for this very insightful talk you gave. And with this, I pass the word to our second speaker, who is Thomas Billotte, the research engineer from Globe Photonics in France. And Thomas will talk about compact frequency reference based on photonic microcell. Welcome, Thomas.
Thank you. Oops, sorry.
The floor is yours.
So I'm Thomas Billotte. I'm working in the company Globe Photonics, and I will present you some things about compact frequency reference based on photonic microcell. So, French deep tech company based in Limoges, about 15 years old, and we are developing we are addressing different market with our technology, which is hollow core photonic crystal fiber. So we are designing and fabricating hollow core fiber on demand at different guidance wavelengths with low loss, about dB per kilometer, and we can also try to work on the modal content and things like this. And we are making what we call PMC, which is the base for all of the module we can propose, like beam delivery, pulse compression, sensing, or telecommunications. So what is a PMC? So it's a photonic microcell. So it's a hollow core fiber. We place a gas inside, and then we seal it here, for example, with a mechanical cell. So it's an optomechanical PMC. We are using it in most of our products. And then we can have what we call all fiber PMC, where the end here is like end capped and connectorized with the FC connector. More using it in our quantum technology unit. So this unit works, could be separated in two. We have, say, our products, so fiber gas cell, and deep tech solution, where we are working in different collaborative project, magnetometry or quantum photon sources. So I will try to address both of this thematic, and I will start with the frequency reference. So to have a good sensor, you need some good frequency reference or some good clock. And I guess most of us know that now the best atomic clock instability are about 10-18. But for some application, 10-13 could be sufficient, but we want something very compact with low cost, low size, low weight, and so on. There is different technology to do that. We have microscopic glass cell, small silicon cell, multipass cell, hollow core fiber, and planar waveguide, like CMOS compatible technology. And of course, Glow Photonics is working on hollow core fiber. So to choose the gas we've placed inside, we look at the recommendation of White and Measurement International Office. And as we can see here in the visible wavelengths, there is the iodine that cover a wide frequency, wide panel of frequency. And this also a possibility to be an alternative for the usual microwave atomic clock with rubidium. So this is 2 papers just to illustrate that the instability with this kind of cell could be quite low, like 10⁻15. And here is our product. So hollow core fiber with low loss at 633 nanometer. We fill it with iodine, and then we seal it with this end cap. So basically it's a sleeve that is collapsed at the end of the fiber. And then we connectorize to FC connection. Now this is the spectrum, the absorption spectrum we can measure. So in red is the standard gas cell, and in black is our PMC. So we can see that there is a 6 times higher contrast at room temperature. All of this is at room temperature. And for the Doppler free signal is the same. We can also see it by eyes. Usually we need some lock-in system to resolve it. Here we can even see it by eyes. So it's quite interesting to lock some laser with that. And we've made what we call cell frequency and land deviation just to have an idea of if we stabilize our laser well or not. And we can see that, yeah, we earn like 5 orders of magnitude compared to free running. So just to summarize this kind of PMC, so it's FC connectorized, it's quite low loss, about 3 dB. Have a high contrast both in Doppler limited and Doppler free signal at room temperature for wavelengths from 500 nanometer to 700 nanometer. Now, another molecule that is of interest for us is like acetylene for optical telecommunication wavelengths. So here is the same principle. So same process, we load the fiber with gas and we seal it inside. But here what we can remark here is the very high contrast of the Doppler free signal. So we define this contrast by the height of this transparency peak divided by the depth of the Doppler absorption. And we can guarantee about 10% contrast of this peak with about 100 milliwatt of pump power in a saturable absorption technique configuration. But we have observed in the lab about 30% contrast for this peak. So it's really high if we compare with in the literature too. And this peak is stable years. We've measured the line width of this peak, and even after 2 years, it's still stable. So the lifetime of these devices is at least about years. We don't know if it's more or not because we do not measure it yet. Fractional frequency instability compared to a locked comb is about 10⁻11 at 1 second and 1,000 seconds too. And here an example of an option we can propose, because even if it's FC-APC connectorized, we cannot directly plug it to a standard solid core fiber, because our hollow core fiber, the mode inside is not the same size, and so it does not fit directly with a standard patch cord. So we need to adapt devices. So it's an optomechanical U-bench, and we propose to pre-align it. Then you can plug and play, but with this module. So to summarize, this one is more or less the same than iodine, but at 1500 nanometers, lifetime more than 2 years, and a very high contrast Doppler free signal. So now I'll switch to our second part of works, which is R&D project, and there is 2 of them. The first one is called ChrysCube. We're near to the end of this project. It's a European project where the aim is to fabricate PMC, but with rubidium inside, because this kind of atoms are quite difficult to manage inside hollow core fiber, because it sticks to the wall and there is a lot of challenges to address. So we've worked on different aspects. For example, on post-process on hollow core, basically try to do some mode field adaptation from solid core to hollow core, Bragg rating to create some cavity, anti-reflection pattern. And more specifically in the hollow core, we've coated the inner wall of the core, trying to create what we call smart coating for anti-relaxation properties, or why not to help the loading of rubidium inside the fiber, because it's, as I said, it's really difficult. It could take months or months and months to load, for example, rubidium atom inside. So we try to address also this challenge, for example, by handle the atoms, place it inside the fiber, or by heating everything. And who said new loading process said also new splicing process or encapsulation process. So we are also splicing with CO2 laser to allow us to seal the fiber directly inside a vacuum system. And another more recent project in collaboration also with different European partner and the University of Glasgow, this project called VMAG. So we would like also to do rubidium PMC and then try to make it as a magnetometer quantum sensor. Would like to not only measure the strength of the magnetic field, but also the orientation based on the mode we can couple inside the hollow core fiber. And then with the orientation of polarization and all of this, we can check at the output of the fiber what should be the magnetic field. So that's it for me. Thank you for your attention, and please contact us if you have any ideas, because I present part of what we can do. And Christopher was speaking about gas cell. I've speak about acetylene and iodine. We can also make with other, for example, CO2. Why not water or other gas? So we really would be happy to collaborate and try to build what would be suitable for you.
Thank you very much, Thomas. Interesting presentation, and that's a great topic, of course, for all kinds of quantum sensing, the hollow core fiber. So we're glad to have an expert on this with us. Let me first ask you to just highlight the typical EPIC question. What is that you can offer to our EPIC members, and what could they do for you to help you in these developments?
So basically, it's the answer to these two questions will be more or less the same. Is like we'd be happy to see what we can do for you. Like if you have any requirement with, for example, gas cell or hollow core fiber technology, we'd be happy to try to collaborate, create some project with you. And we are interesting for people to test our product, to have so and see what we can improve, what could be the next step for development.
Okay, well, fair enough. Any more questions from the audience? Okay, we have one from Alessio representing Science Getters. Go ahead, Alessio. You can unmute.
Okay, can you hear me now?
Yeah, that's good.
Okay, thanks. Thanks for the opportunity to talk. Thank you very much for the nice presentation. And I can see from this presentation and also from the previous one that one key point is to introduce small amounts of rubidium atoms or small amounts of alkali metals that are the active elements inside the cells or inside the hollow fiber. And at SAIS, we are working and studying advanced material solution in order to allow the introduction and the dosing, microdosing of very small amounts of atoms inside small devices. So we are studying the possibility to use some special precursor in order to provide very tiny amounts of these atoms, not only for rubidium, but also for cesium that is used in atomic clocks or in other devices. And so we are open and we are looking for partners in order to develop some solution that can well fit even with the very small applications. So this could be a small contribution also from the supply chain that is dealing with the material side.
Okay, thank you.
Anything you want to add, Thomas?
I mean, for the small amount of rubidium for in our PMC part to fabricate this kind of device, we are more in let's say lack of rubidium. We need a lot because we lose a lot on the wall. So we prefer to have a lot, but why not for detection or something, or why not creating some smaller core size or things like that to try just to detect on the small pieces of fiber? Why not? We can try to develop this aspect. So could be interesting, yes.
Okay. Let me take the opportunity to ask you quickly, what's your take on also on the communications with hollow core fiber? Is there any route towards reducing the cost of production for this?
For this, I cannot say really for the price of hollow core fiber. For the because I'm not the one that deal with the price in the company, but yeah, we are working, of course, on making a longer distance when we are fabricating hollow core fibers, in order, of course, to be more competitive with the price comparing to solid core and other companies. But at this point, we are more selling like patch cord of some meters than really kilometers of fiber, you know. So we'll see, probably. For the PMC, we try also to decrease the price, of course, because I know like gas cell is more about like hundreds of dollars or euro. And for us, we are a little more expensive, but I mean, we try to match the market also on this point, but let's hope with better properties.
All right. Fair enough. Okay. Well, thanks again, Thomas, for joining us. And
Thank
with
you.
this, I pass the word to our next speaker, who's Marco Nordman, the product manager representing QNAMI.
Hello, everyone.
Welcome, Marco.
Hello, do you hear me?
Yes.
Good, and
We hear you. And
now you should see it. All good?
Coming in a second.
Let me know when you see it.
Still coming.
Okay, I see it already.
We can see it. Ivan, can you see the presentation?
Good.
You see it? Okay,
please.
good.
Go ahead.
Great. Yeah, so thank you, Ivan, for inviting me again. I had the pleasure already joining you 2 years ago, I think. And there was already the question on what quantum imaging is, and I hope I can give you a glimpse of how we interpret quantum imaging. And here in particular, I want to speak about how QNAMI's scanning NV microscopes help to bring quantum sensing or imaging to industry. And the images you see are not abstract art or anything, but it's rather the visual proof of what resolution and insights you get with our technology into magnetic properties of materials at the nanometer scale using quantum sensors. To be more particular, what you see is basically a part of a memory chip you have or you might have in your smartwatch, and you see the individual magnetic states on so-called MRAM bits. So what I'm going to talk today is about the revolution that currently happens in the semiconductor industry, or the shift in semiconductor industry, and how we are proposing here a metrology technology that might help here to bring semiconductor industry forward. And well, my slides also start switching. Yes, what I want to start with is basically a testimonial from Sebastian Quet, the founder of Vertical Compute, who is one of our first industrial users, together with IMEC, using our system to measure and qualify their devices. And what this statement represents is perfectly the mission that we are trying to provide precision tools necessary to accelerate the innovation and overcome the mounting challenges that appear to be in semiconductor industries today. Challenges are manifold, and here are just some I want to highlight, namely that the current computing paradigms that helped us to see the technological progress over the past few years come now to some limiting limits. Firstly, about this year, we have about 40 billion IoT devices creating a tremendous amount of data that require very efficient and very high-performing hardware just to cope with all the data that is generated day to day already. And if you look into the future, already by 2030, it is expected that about 20% of worldwide electricity is consumed by such devices. And to make sure that we can use the benefits of information and communication technologies also in the future, energy consumption needs to be something that is sustainable. And further, another thing that has driven technological advancements over the past few years is Moore's law, but that slowly slows down or keeps slowing down over the past couple of years. And this particularly becomes apparent when you look at the fabrication costs that rise about 30% per year, that hinders innovation and the technological progress when you implement new devices or new technologies. So to make this progress not slow down and to tackle some of these challenges, industry now aims to look at new types of technologies to implement into technology. For example, we look now for technologies that employ spin over the charge for data handling and enable a fundamental shift in how we store and process data. These memories are then supposed to be non-volatile and energy efficient and also offer high-performing data storage and processing. They are supposed to make cloud computing more sustainable, and in the future, people hope that those will enable neuromorphic computing that bring AI directly onto device, everything that basically runs under edge computing. Some of these technologies are what's called spintronics, and others are, for example, magnetic memories, for example, MRAMs, so magnetic random access memory, where you basically have a bit stored in the magnetic states of a device that is composed of multiple layers. Now, this is where quantum sensing steps in and where QNAMI can unleash its power, namely by our quantum diamond probes that have a single engineered defect, atomic defect within the apex of those diamond probes you see in the middle. In particular, these defects are so-called nitrogen vacancy centers that act as an atomic scale quantum sensor. What makes those probes so special is that they work at room temperature, which is crucial for industrial applications. They are built on a scalable industrial manufacturing process, and they offer enhanced resolution and sensitivity, allowing to capture magnetic signals of even single atomic layers. Those NV centers leverage basically the quantum properties of an electron spin that is manipulated by a laser and a microwave to precisely measure local magnetic fields when you move this probe over the surface of your device under test. Based on this, QNAM provides a unique and compact scalable quantum microscope platform that is suitable for sensing applications that allows you access to magnetic information not accessible before with a nanometer resolution. The array of images here again is like a larger view of the images you saw at the beginning, basically show individual bits with a few hundreds of nanometers spacing. And by imaging those MRAM bits mid-process, you are able to detect defects, failures, optimize processes. So what we're building on top of our own quantum sensors is a dedicated turnkey scanning NV microscope platform. It covers a wide range of applications. On the left, the first product we released is our Proteus Q, quantum sensing microscope designed for room temperature operations. It's used in mostly research and semiconductor R&D, and has about 20 publications so far alone in 2024, 2025 alone. So it's used in multiple research topics. Some are spintronics, but there are also other application areas like current sensing, 2D materials, or bioimaging. And this year marks also the launch of our low temperature version of our turnkey scanning NV microscopes. That then holds the promise to investigate and learn more about 2D materials or nanomagnetism at the more exotic temperatures around 2 Kelvin. Both systems have in common that they're basically SPM techniques, so scanning probe techniques, allowing you this very high spatial resolution and high sensitivity. Beside magnetic properties, what you can also investigate are currents, current flow, or local temperature or RF sensing, which is basically imaged here, current flow in a small conductor, which indicates then defects in those conductors, or radio frequencies propagating through a conductor and giving you a sense of what the power distribution is within those conductors. To be more specific on where this is used in industry is highlighted here in this collaboration we currently have with IMEC, where a tool is used in a process of manufacturing those MRAM devices, and where it used to be a blind spot in the manufacturing process after etching those MRAM bits, with scanning NV now having access to the manufacturing quality of the individual bits. We also have another collaboration with the European 2D pilot line as part of the European Graphene flagship, where we are also trying to bring scanning NV as new metrology tool to more industrial scale manufacturing of those 2D materials to perform correlated failure analysis or defect statistics. So who we are basically is a small team composed of microscope experts, quantum sensing experts, with facilities in Switzerland, so in Basel, or close to Basel in Muttenz, and then our quantum foundry in Villingen, where we do our own quantum sensors, or the diamonds. And yeah, that's already the end of my talk. Thank you for your attention. The typical EPIC question might be, what can EPIC do for us, or EPIC members? We are in need of lasers. We heard that before. Everyone needs lasers, but also photon detectors. And what we really need is applications. So if you see or have a problem that is expressed by surface magnetic fields or surface magnetism, that is something we'll be very much interested in using and testing on our microscopes. Thank you.
Thank you very much, Marco. Great presentation, and indeed a very impressive technique. Having this single NV center on top of a diamond tip sounds very sophisticated. And that actually brings me to the first question. How industrially scalable actually is the production of such a system? Or does it require a lot of manual preparation of the tip?
The tip itself is something we manufacture in the thousands. And right now, because the usage is limited by the instruments we have to supply, it's a semi-manual process of picking those tips that are available in the thousands and mounting them to the probes. But that is a process that you can fairly easily automate. It's not more challenging than mounting small micro lenses, for instance. So if the demand rises, then the step to fully automating those probe manufacturing is possible.
But so that is with just diamond tips, but having this single NV center on top of a tip, how is that actually made?
Okay, so the NV center inside the diamond tip is part of the manufacturing process. So you have thousands of those devices, most of them having a single NV at the apex of their tip. So you manufacture that from bulk diamond, and then what remains is this nice pillar structure that has, where some have then this NV.
Okay, so it's actually introduced during the diamond growth process.
During the diamond, afterward, yes, during the diamond growth process, and then there are some treatments that need to happen to make sure that you have that as centered as possible and as close as possible to the apex. Yes.
Okay. Yeah, that sounds like a very sophisticated process. So yeah, so that's fascinating. You have handled this, and it sounds like it must have a lot of other applications from what you have mentioned. Maybe I hope there will be some questions coming to you afterwards from the relevant industries, specifically semiconductors, like you mentioned. Is there any other industry of interest you can specify?
So we'll hear a couple of other talks of technologies based on NVs. So what the capabilities Qnami offers is also customizing those NV diamonds. So while our instruments use probes as a single NV, what we managed and grown in expertise is shaping the diamond to implement microfluidic channels and localize where those NVs are. So if you have companies that use it for, I don't know, flow cytometry or other applications where you want to measure locally magnetic fields of plasma or something else, blood, for instance, that is something where we can supply, yet we're looking then for industrial partners to make those devices, shape the diamonds, and then being a customized diamond provider.
Okay. No, that sounds very, very interesting indeed. Is there any further question in the audience for Marco? Take the unique opportunity. Okay, if not, I'm sure there'll be questions coming later. So thank you very much again, Marco, for your input. And with this, I pass the word to our next speaker, Nathalie Olivier, who is a sales director for quantum sensors, navigation, and motion simulation systems at PHIX. Welcome, Nathalie. Whenever you're ready. I don't hear you though. Could you check your microphone? No, still there's no sound. You might need to look at the bottom left of your Zoom screen. There is a little arrow next to the microphone. So you push the arrow and then you select the microphone you want to use.
Is it better now?
Yeah, now we hear you.
Yes, good. Sorry for that.
No worries.
Yeah.
So yeah, so please, yeah, you can share your slides and the floor will be yours.
Okay. So it should be okay now. So I'm Nathalie Olivier, leading the quantum sensor cells within Excel.
Yeah, excuse me,
yeah.
Nathalie, we don't yet see your screen. Please check if you're sharing it.
Yes, I did it.
Okay, now it should be coming.
Oh, okay.
Mm-hmm.
Okay.
And you might want to speak a little bit louder. Thank you.
Okay. I will try to. Do you hear me now? Okay.
Go ahead.
So as you said, I'm leading the quantum sensor sales within Excel. And of course, it's a pleasure to be here today with you. to talk about the subject of quantum sensor, and I will show here how concrete it is for Excel. So Excel is a fast-growing high-tech company, French-owned, more than 2,000 employees now, on more than 300 million of turnover. We are experts in maritime, robotics, navigation, photonic and space application, from the deep ocean to outer space. A part of our DNA is coming from inertial navigation systems. So these systems are composed of in-house sensors and intelligence, fiber optic gyroscope, accelerometers, advanced processing algorithm. But even with the best design, navigation system can drift over time. So that's why we need absolute references to correct this drift. And gravity is still today as a key positioning data, a key positioning information. So why gravity? Because gravity is like the Earth's fingerprint. If you can measure very precisely gravity, then you can use it as an information to correct your position. This is today key information for maritime application in case of GNSS jamming and spoofing. But navigation is not our client only focus. Gravity is also an important field, of course, of scientific observation. And that's where today many of our clients are deeply involved. That's why even if we are invested in quantum inertial navigation through scientific collaboration, for example, with LNE in France, Institut d'Aquitaine, on the X-Atom project, or on board Gravimetry with Onera, for example. We are today among the leaders in geophysics application using quantum technology, thanks to the AQG design in collaboration with the CIRT in France, so Observatoire de Paris. So the AQG, what it is, it's a robust and transportable absolute quantum gravimeter. It's based on the free fall of the mass obtained by cooling rubidium atoms. This high-resolution gravimeter proved its performance today on the field, from the mountain plat to Hawaii, from the Zivio to Antarctica, or from Greenland recently to Guadeloupe. And it's deployed by scientists who are not familiar with quantum technology. And this just because we design this system to be user-friendly. These deployments and many instrument intercomparisons are assessing the high performances of the sensor, reaching a resolution of 1 microGauss, so an acceleration about 10 nanometers per second square. And today we are above, we are about nearly 20 of them that have been manufactured. And the plan is to deliver 8 of them in the coming 12 months, in this coming years. So what is exciting in this technology, in this market, is not just the technology, but the application. and we are investigating mainly the geosciences, field application, often on harsh environments. So that's where the A2G shows its true value today. One of them is understanding water dynamics. We are also deployed on the top of Etna volcano, on many other volcanoes, to monitor the mass and the evolution of the magma chamber a long time. We are also trying to explore underground resources. Sorry, and we are not trying to detect subsurface objects or structure, such as pipes or cavity underground. And we are on the metrology application too, for the comparison of other gravimeters or for monitoring reference points. So the expertise we've built in laser technology for atom manipulation is also at the heart of XL quantum sensor. Within this division, we bring together a complete instrument range of quantum sensors, such as atomic clock, optical frequency transfer system, and of course our gravimeter. Inside this division, we are designing and manufacturing the critical building block to manipulate cold atoms. So it's intelligent laser system, IMOB, integrated micro-optic benches, and others high-end optical components. We vertically integrated our own tier photonic chain, and this from the design to the production. In conclusion, at Excel, we are very proud to be at the heart of this technology by transforming quantum physics into practical instruments that are on the field and help to explore, protect, and understand our world. And to sum up, quantum gravity sensors are mature today and operational inside Excel portfolio in the domain of geophysics. Excel offers a portfolio of lasers and components for atom manipulation and quantum applications. And we are now facing new challenges. These challenges are to go from static system to mobile systems. We are part of European funded programs such as the PHIX project, and you can see the picture of our differential quantum gravimeter. It's going to be a mobile and autonomous system. And we are also, as I told, on board Gravimetry program for airborne and seaborne survey. We are open for collaboration within this community, especially in geophysics and mining and resource exploration application. As I show you on the application, we really need to explore the market of oil and gas, CO2 storage, resources exploration. And for this, we need to work with a survey company or with services company to help us to go on real application and test our system in real. So if you are on this market or on this technology, you're welcome to work with us. and what we can bring to this community. Maybe maybe there's some of our laser component that could be integrated in your platform or system. And feel free to contact us. We could design together maybe the solution you need to design your own instrument. Thanks for watching. It's okay for me.
Right. Thank you very much, Nathalie. That's a great presentation and very exciting developments, this gravitometer. I only wish we could hear your beautiful voice a bit better, but this will leave for the next time. Is there any question in the audience for Nathalie? And I'll ask just a quick, short one from me. I'm wondering, so you mentioned this airborne and seaborne systems, but that must be also a topic for the space explorations, isn't it?
Yes. So we are on board the Carioca program on laser application. We can do it by ourselves, of course. It's a huge program. It's a costly program. But yes, we are in.
I see. Yeah, that sounds like a very exciting tool to use also in the astronomy. Okay, if there's no further questions, I mean, Nathalie, you described very well also what you can do for our members and what they could do for you. So I'm expecting a lot of feedback to come afterwards. So I'll be happy to put you in contact with Nathalie if you wish. So we'll keep this for later. And now I think Nathalie, and I pass the word to our next speaker, Andrei Adelin, the CTO and founder of Novovis. Welcome, Andrei.
Yes, thank you for having me. Can you see the slides?
Yes.
Okay.
We see you, we see the slides,
Perfect.
and the floor is yours.
Okay, thank you very much. So I'll be giving you a brief overview of our product based on SPADs that were mentioned by the first speaker. We are a Swiss company based in Neuchâtel, and we are a fabless semiconductor focused on computational SPAD imagers. So we design and develop these circuits in order to facilitate entry into the SPAD detector market. So a brief overview of SPADs. There's a special type of photodiode that operates above its breakdown voltage and has this three-step cycle that you see on the right. When the moment the photon hits the detector, we have a spike in the current that we need to quench to avoid damaging the device, and then we recharge the pixel to bring it back above excess bias. And this is a very fast cycle that takes a few nanoseconds to go through. And we can run this continuously for these pixels. And the way we interface with them is by putting a very simple inverter after it and essentially transforming the SPAD into a digital device, because that pulse is directly converted into the digital domain, which means there is no readout noise in these devices. We only have dark counts. And like I mentioned, this process is very, very fast. So we can count hundreds of millions of these events per second for each of these pixels, which gives us a very high dynamic range, because the noise floor is in the order of tens of counts per second, and then the top is hundreds of millions. And we do not saturate. These devices do not hit a ceiling, but they essentially keep counting. So if we have enough time and we integrate for enough time, we can extend this dynamic range, or we can extract the incident photon rate based on what we measure at the output. And an extra benefit is the picosecond jitter. The jitter beat from the moment the photon hits the diode, and the edge of the output pulse has a picoseconds of jitter, which allows us to use these SPADs for time of flight, which is was the main driver for this technology and is currently being used like this in commercial products, like the face recognition in Apple products or laser distance measurement. And more recently, they've been used now in surveillance because of their single photon sensitivity. But in this case, we lose this single photon information from the pixel, and I'll get into more detail a little bit later. But the problem with these cameras and what's currently hindering their adoption is the data rates, right? Like I said, we're measuring hundreds of millions of events per second per pixel, which results in a ridiculous amount of data. And this is an example of a detector that was published in 2017. So this was most likely the design like more than 10 years ago. And even at that time, it was producing 3 gigabytes per second if you were to run at full speed, which exceeds common interfaces and poses severe bottlenecks. So what's currently being done is either you operate these sensors in bursts of a few seconds, or you slow them down just to lower these data rates, or you sacrifice that single photon information. And by this, I mean, for example, you can count them on the device, and then instead of getting this photon hits, you get a photon counts over an integration period, which essentially turns it into a very sensitive camera, but you lose that timing precision of the photon. Apart from this, they're relatively complex. They were developed in academia. They're now scientific cameras, so they were designed for scalability or ease of integration into industrial products, and they have a higher cost compared to other alternatives because of these high-performance electronic components that need to be integrated into them to support that very high data rate. So that's where we come into play with our computational SPAD sensor. So by computational, we mean that we've integrated pre-processing electronics into the same the sensor, right? And edge computing, if you want, where we process this raw data from the pixels directly on the device and extract that relevant information, thereby reducing the burden on the system, allowing it to be easier to integrate, reduce the power, because even now the majority of the power consumption from these cameras comes from the IOs that toggle at these very high data rates. And by pre-processing in parallel on the device, this allows us to have a significant increase in speed, in acquisition speed. So an example on our flagship product is our asynchronous detector. This is a 3000 pixel camera that has an event-driven output. So we've eliminated the raw output of the SPADs, and instead the camera only sends out photon hits. This allows us to be able to reconstruct the frame rate, if we wish, at up to 100 million frames per second, making it the fastest SPAD array of its kind. And it's all done over the USB 3 because of this high level of data compression. So if we were to look back at the plot I showed before, even at this small resolution of 3000 pixels, if we were to operate at full speed, we'll be above the data rates of even upcoming interfaces. However, by doing this pre-processing on the detector itself, we're reducing this by 2 orders of magnitude, and now we can operate it continuously with conventional, very easy to access interfaces. This also offers a path for miniaturization. You can see the camera in that picture. It's a 3 centimeter cube because there's no longer a need for this high performance electronics around it. Everything is on chip. The hard work is done on chip, and then externally we just control it as a normal detector. So what does an image capture that 100 million frames per second look like? Well, this is a 3D plot showing these live photon hits on the detector surface. You have the X, Y, and the time direction. You can see the photon hits as they arrive on the detector. And then if we were to slice and freeze one of these moments, we would get an image at 100 million frames per second, which is very underwhelming because at this very short exposures, right, the scene needs to be fairly strongly illuminated to be able to see something. So what we do is we add we can add these frames together to increase the exposure until we get an image that is that looks as we'd expect it to look. But then the question is, why do we need to operate at 100 million frames per second if in the end we're compressing it? Well, the answer is because there's a lot more information in these frames compared to the lower speed. Right? And an example here, two examples here actually, are of software-defined cameras. If we take this raw data captured at this very high frame rate, we can process it in software to emulate different types of cameras on the same data set. On the top here, you have an image of a scene where we have cars moving on the street. And of course, if you should all be familiar with taking a picture of a moving object, it becomes blurry. But if we simulate movement of the imager itself, then we can selectively focus on different objects in the scene based on their speed. Or in some other, if we use a more exotic shift of these binary frames, we can actually keep all of these objects in focus at the same time in the image. And on the bottom, you see an event information overlapped onto an intensity image, right? So an event camera combined with a normal imager on the same data set done live in with this data sets. So this is these are a few examples of what can be done by processing the streams of data. We've also demonstrated data compression algorithms or other camera modalities, and these are all run on one of our prototypes that has this the capability of running software, user-defined software directly on the behind the pixel, so no longer application specific like the previous array. Additionally, we also have smaller sensors. These are 1 or 2 pixel detectors that are designed for specific applications. The processing is specific to, for example, performing correlations between individual pixels or resolving the number of photons that lands on the detector. So no longer events, but more application focused or designed to interface with external hardware. And this is an example of such a device is a photon number resolver, where we have a cluster of SPADs that act as a single pixel, and then the digital circuitry on the chip detects coincidences and outputs a pulse on a dedicated output. If we have 1, 2, 3, 4, or more simultaneous photons that fall within a nanosecond window. And each of these SPADs can operate at 300 million events per second. That cycle is happening at 3 nanosecond periods. And on the bottom, you see an example where we've directly coupled this detector with a photon counter, like with a time tagger, so 4 channels simultaneously. And by counting these pulses, we can essentially see a hand diagram. We can see the Poissonian distribution of the photons as they land the detector while we adjust the laser intensity. And the curve that you see there is not fitted. It's actually just a direct plot of a Poissonian distribution that has the same average photon count as we measured, and it fits very well at the low light level. And then as we tailor off to the higher photon rates, because we're collapsing the bins, we see a slight deviation. But this is done without any comparators. There's no external circuitry. It's just counting pulses directly outputted by the chip. So the future is in fully customizable on-chip processing. I already mentioned some of the algorithms that we could run on our prototypes. And the direction we want to push SPAD imagers into is to have the ability to run custom code on the detector. And this gives extra benefits, right? We're further reducing the power consumption and making it easier to integrate into system. And ideally would want a detector that's just a plug and play replacement for other imagers, or where people develop their application or their system, they will no longer consider SPADs as being very difficult to handle. In case, just treat them as any other imager. And here in the picture, you have the prototype I mentioned, where we have an array of independent processors designed to directly interface with the SPAD pixels on top and process that data in a parallel fashion. So thank you very much for your time, and I'm open for questions.
Very nice. Thank you, Andrei. It's great to have your presentation for the first time with us. And indeed, it's a very powerful technology you have developed. I'm actually wondering, how does it compare to the other approaches to making single photon detectors? Could you make a little comparison?
So in terms of SPADs, we differentiate ourselves in the sense that we are non-application specific. We focus from the beginning to making it for industrialization. Our devices were designed with this in mind, and that's why we have this very small form factor. The packaging is done so that it's friendly to integrate, etc. And so that's what sets us apart. And we are targeting more of a general off-the-shelf SPAD sensor market. We don't focus on SPADs for LiDAR, for example, because we want to expand SPADs into other fields where so far have been difficult to access.
Okay, I see. We have a question from Chris here that I actually expected. Please go ahead.
Hi there. Thanks for the talk. That was a great talk, and I have an interest in SPADs, as you could probably tell from my talk as well. So the thing that caught my attention was you talked about event-based as well as conventional imaging. So just can you do that simultaneously? You suggested there's an element of post-processing there, and how close in terms of from a time frame can I understand those two, and what's the computational load that I would have to understand those two? Can it largely be done on chip, or do I need some kind of FPGA, for example, to manage that?
So for now, the device that we showed only on chip only performs the event processing. So you'd get this raw stream at the output, and then everything is done off the detector. But since it's a stream, it's very easy to process. In this particular case, for the event camera, because you continuously increment the values for a specific pixel to figure out if there is an event or not. So it's not resource intensive. It doesn't need GPUs or FPGAs to run. But of course, it's a new, the problem we've seen is that it's a new type of data, right? So now the struggle is more on the algorithm side to develop algorithms that can efficiently process single photon data streams. But I wouldn't say that's a bottleneck in terms of processing power.
And just two, I suppose, follow-ons from that is that have you done much in terms of overlaying your SPAD onto a sort of a more conventional CMOS approach? I'm thinking if I had a setup where I just had a beam splitter effectively, and I'm doing LiDAR time of flight using your system, but as an overlay, would that be something that you've seen before?
Not like that. We've seen hybrid arrays where we have some SPAD pixels designed for time of flight, so they have the time stamping circuitry in them to capture at picosecond arrival times, and combined with conventional SPAD pixels that are just used to integrate counts. So there are these types of detectors, and then you have of course a lower resolution 3D map, and then the intensity simultaneously on the same detector. So there's no beam splitter involved. It's more of a hybrid architecture.
Yeah. Okay. And then I won't ask you to say it now, but if you could email over your pricings, I'd be interested.
Yes, definitely. Okay.
Brilliant. Thanks.
Thank
you. That's the spirit of the EPIC meetings. All right. Is there any more questions for Andrei here? If not, I suggest we keep the timing. We thank him again, and we switch to our last speaker of the day, Travis Scott, who is a business development manager at Fintech, and we will switch gears and talk a little bit about the instrumentation, I guess. Welcome, Travis.
Hello, can you hear me okay?
Yes. whenever you're ready.
Okay, can you see the screen?
Yes, it's coming, and the floor is yours.
Okay, so thank you for all the great talks so far. They've been very interesting. So I'm here on behalf of Finetech. So Finetech is a submicron die bonding equipment supplier, and we offer tailored equipment and process development. And we're starting to focus in on the quantum technologies world. The way that we see quantum technologies is kind of an evolution of existing technologies. So just lasers, photodiodes, ASICs, FPAs, all these kinds of things that have already been in the optoelectronics photonics industry for quite some time. So yeah, what we see is we've got these 3 or 4 different quantum technologies, such as quantum processors based on like ASICs or MEMS technology, lasers and single photon diode, single photon sources and detectors, such as VCSELs, APDs, edge emitting lasers, and so on. And then the optics and optoelectronics for quantum communications, QKD, photonics, and PHIX technologies. And what that means by Finetech is our bonding technologies drive these various different assemblies in the quantum technology products themselves. So thermal ultrasonic die attach, adhesives, eutectic bonding, and so on. So we see quite a lot of different technologies coming through Finetech, and we just offer this assembly and prototyping and building service, as well as the machines to manufacture those parts in the end. So I won't go too deep into all the various different technologies. I think we've seen enough examples of that today. But what I wanted to do is tie some bonding technologies to end applications. So for example, gold-to-gold thermo or ultrasonic die attach. We see this in a lot of source VCSEL or photodiode assemblies. So where you have these very small components that need a very strong electrical mechanical attach. We also support this with laser bottom heating, thermocompression bonding, as well as ultrasonic friction welding or friction bonding from the top side. The next technology is adhesives and epoxy applications. So this is a big part of optical communications, quantum communications, PHIX, anything that goes into the side of like laser light or photons and so on. So again, this comes up in source lasers, the coupling into fibers, the coupling into lenses, as well as any kind of passive optics that happen between lasers and photodiode side. This also goes into actual like chip attach. So anything that goes into wire bonding later will generally have like silver epoxy and reflow. So this can also be done in the same system with a very similar setup. And then we have the indium bump interconnect. So this is a specific technology for quantum processes, for quantum computing more. So superconducting spin-based processes. But we do see this more and more in different applications now as the kind of fundamental technology is maturing. But this is generally for much larger chips, for like RICs and larger functional chips themselves, so ASICs. And indium bonding is also applied for some edge-emitting lasers or laser diode laser bars. And then for thermocompression bonding or eutectic soldering, we see this with a lot of gold-to-gold applications and anything that requires a very high electrical throughput or thermal conductivity. So like edge-emitting lasers and any sort of high-power devices or pump sources and that kind of thing. What you can see here on the left is a thermocompression bonding of a chip to a RIC substrate with a gold interconnect. And then on the right-hand side, you can see the laser bar in an indium or gold tin solder. And then I just thought we have a video here of our newest femto, or our newest machine running. And I'll just talk over it as it's running. So what Finetech can offer anyone from the EPIC environment is process support, process and application development, and consultancy. So we deal with a very wide spectrum of applications, technologies. Some of them are quite standardized and simple. Some of them are much more complex and custom. And what you can see here is something that we're trying to standardize, which is the ultrasonic die attach of VCSELs or APDs onto substrates. And the next part of the video that you see running now is just ultraviolet die attach with an ultraviolet epoxy for any kind of active or passive optics or optoelectronics. So we offer this application as a service, which we also then transfer onto any kind of system purchase that comes later on. And any system that is purchased generally comes with a running process on that system. So you just get the machine landing inside your factory, and then you press the green button, and technically it should run. That's the theory anyways. But yeah, so this is the new system that we're bringing to the market this year as a kind of higher speed production version of our current Femta 2. And then in the coming year, we'll be bringing out a gantry or a portal system for much higher volume production, but with a reduced accuracy of the fine placer line. And yeah, just to round it up, just tying it back again. So we serve the quantum technology market on a basis of our existing bonding technologies and application experience. So what we do is we take our experience with our different modules and our high accuracy automated or manual systems, and we deliver that into R&D or production environments that are growing into these quantum technology directions. So if there's anything that we can do for you, please feel free to get in touch. And if you have any questions, please feel free to ask.
Thank you, Travis. That was a very interesting instrument you've shown us, and interesting capabilities for building the packaging for quantum sensors, of course. Is there any specific question to Travis? I think the packaging is also sometimes the last thing people think of when making those sensors, but it is actually a very viable part of the final system. Could you maybe tell us, Travis, a bit more about the portfolio of products that FineTech provides? Also
Yes,
for
absolutely.
quantum sensing, but not only.
So we offer a full range of equipment. So from very simple manual tabletop systems that can still achieve submicron alignment and placement. And on this tabletop system, we have almost the entire module variation that we can put into the automated systems. So formic acid, high temperatures for reflow, adhesive dispensing, ultraviolet curing, and so on. And this range then moves up to semi-automated die attach equipment in the submicron accuracy range, and then into fully automated die attach equipment. And like I said before, this is the full module set, as well as application support, application development as a service in addition to the machine. And then in the future, we're moving more towards this inline capable production equipment with a similar kind of philosophy for modularity and accuracy.
Okay, good point. Any more questions? Okay, if not, I suggest we thank Travis one more time, as well as all the other speakers.
Can I ask one question to Novaviz? Are you building your own equipment, or are you purchasing it from a supplier?
No, we're not building our own. So we don't manufacture the silicon in-house. We just use the conventional foundries. The only thing we do in-house is the final assembly and testing.
Okay, great to know. Thank you.
Okay, so if so, yeah, I think we will come back to you with interesting questions afterwards from everyone who will watch this video offline later. And yeah, so we thank Travis as well as all the other speakers of today's session. Let me share just a few quick messages with you, all of you. So this was the EPIC Online Technology Meeting on photonics and quantum sensors for you. I'd like to thank again Christopher, Thomas, Marco, Natalie, Andrei, and Travis for making this a very fruitful meeting with sharing a lot of insights with us and just showing us the beauty of quantum sensing field. So if you all liked this video, I also want to bring your attention to another meeting we'll have very soon. It will take place close to Copenhagen in Denmark on the 2nd of October, and this meeting will be offline. It will take place the day after the famous ECOC Optical Communication Expo in Copenhagen, and the meeting will take place at the headquarters of NKT Photonics, which is also a very interesting company to see from the inside. So we will have a very intense program spanning from quantum communications and quantum computing to, of course, quantum sensors and photonic chips used in the quantum. We have a lot of very interesting presentations coming, including the keynotes from NKT, from British Telecom, from Yole Group, and as well as Fraunhofer HHI, for instance. So we're now close to close the agenda and the pool of invited participants in this meeting. So please don't miss the chance to register as soon as possible, and hopefully see you offline on the 2nd of October. So with this, I just want to remind you that EPIC, the European Photonic Industry Consortium, is there for you to share the technology expertise, to help you with market studies, provide networking opportunities, mentoring, marketing and recruiting opportunities, as well as help you with investment. So now on your screen, you have this online poll that appears to give us some feedback about this meeting. So we'll appreciate your opinion. And I also want to highlight the team of EPIC that made this meeting possible. And with this, I'd like to thank you for your attention and hopefully see you next time on the EPIC online technology meetings. Thank you very much.
Thank you
very much.
Thank you.
Yes, thanks everyone for sharing, for joining, and